Okay, so once more, we just asked to calculate the force, vector force for the force exerted by charge Q1 on Q2 for this figure that we used earlier. Okay, and it's off the screen, but this charge is 0.004 coulombs, this negative 0.002 coulombs. This point, I think you can see, is negative 3.210.7. These are in meters. So, well, how do we calculate the vector force? We do the KQ1, Q2 over R squared, and then we multiply by the unit vector, R12 over magnitude of R12. That gives us a vector in the appropriate direction. And we'll see how the direction does work out appropriately. So, you should proceed with the calculation if you haven't already. Okay, well, using what we've already calculated here for the R vector and its magnitude, we get the R over R, and that would be the R12 vector, the vector from here to here. The vector that we used here turns out to be the R12 vector. So I can acknowledge that on the picture. That is the R12 vector because it goes from Q1 toward Q2. Now, the Coulomb's law is here. We've explained that. We've seen that. So it's simply a matter of substitution. We find the KQ1, Q2 over R12 squared right here. And then the R12 over the R12 vector over magnitude of R12 is right here. So it's all very, very nicely laid out, straightforward. All we have to do is do the calculations. So if you haven't already done so, you should proceed to do so. Pay careful attention to the units and how they work out. And actually, I've got something wrong up here. The 13 and the 5 being the X and Y displacements here, that should both be meters. That should be 13 meters, and that should be 5 meters. The units aren't going to work out if I don't fix that. I'll write that down before we go on with the next step, but you should go ahead and do the calculation, being sure to not make the mistake I did, leaving the units off of these quantities. Okay, I've inserted my units up here, and you see that this is going to have units of meters divided by meters, and this is going to have units of meters divided by meters as the denominator divides into both terms of the numerator. Well, the calculation is fairly simple. Now I've approximated it. I've done mental approximations. Square root of 194 is almost 14. 13 over 14 is about 7% less than 1. So it's about 0.93. Okay, give or take. And 5 over 14 would be about 0.36, and even if that's like 13.9 something, I think it's still going to be like 0.36. And this makes a certain amount of sense if you're checking. You want to square this. Well, the square of 0.93, square of 0.9 is 0.81, square of 1 is 1, so that's going to be about 0.87. 36 is an easy number to square if you've done it a bunch of times. It's I think it's 1296. 9 times 144, yeah, I think so. So that's going to be like 0.13. That's going to be like 0.87. So that the squares of these add up to 1 or very close to. So I'm fairly comfortable with my approximation there. 4 times 2 is 8. 8 times 9 is 72. And I've left off my minus sign, which is really important. I need to insert that throughout. Okay. Take care of that before we go on. That's a big, long minus sign there. I don't know if there's anything I can do about that. Let's see. Yeah, that was a little better. Okay, now, approximating this, 72 over 144 would be, well, 72 over 200 would be 0.36. That's about 3% less. Actually, I probably ought to modify that to about 0.37, but I'm not going to do it. I think that should be about 0.37. In any case, that divided by that is like 0.37. I've got 0.38. Let's not worry about that. Now, and that's times this same vector. Let's look at the units. I've got coulombs squared here divided by coulombs here, so that I don't have any more coulombs left when I get to this point. Now I've got meters squared here. If I square square root of 194, I get 194. If I square the meter, I get meters squared. This meter squared will divide this meter squared, leaving us just newtons here. It's the only unit we have left. So when we distribute through here, we're going to get newtons on both components. If I multiply 0.38 by 0.93, well, 7% of 40 is almost 3, so we're going to go down by about 3. That probably ought to go down to somewhere between 340 and 350 newtons. I think the 135 newtons is close, within plus or minus a few. So there is our result. Now, these are the components of the Coulomb force that's exerted up here. So I'll just draw a little picture to represent that. Okay, so picture indicates Q1 0.004 newtons at negative 3 meters 2 meters. Q2 is negative 0.002 newtons at 10 meters 7 meters. F12, now we know that F12 should be a force of attraction, so that Q2 should be attracted toward Q1, so that the vector should go in this direction. But we don't need to know that to calculate it. When we calculate it, it will come out in that direction. Okay, the F12 is approximately negative 350 newtons times I minus 135 newtons times J. Well, that's pointing into the third quadrant, as this vector is, and the X component is over twice as great as the Y component, which pretty much fits this picture and this picture if they're to scale. Now, we can do a further check, and it's really worthwhile doing that now, so we have a deeper understanding of just the mathematics of these calculations before we talk too much about the physics. The angle of this vector should be equal and opposite to the angle of R12. The angle of R12 is arctangent of 13/5. What's the angle of this vector, and does it match the or is it equal and opposite to the direction of this vector? So you should do that calculation. Before I cover this up, let me point out and admit my error. We never used it for anything until we got to here. And in calculating this, I realized what I'd done. The angle of this vector is the arctangent of 5 over 13, not the arctangent of 13 over 5, arctangent of the Y component over the X component. I couldn't figure out how this didn't come out the same as this. But anyhow, let's see how we resolve that over here. The question is, does F12 have direction that's equal and opposite to the direction of the R12 vector that we have from negative 3,2 up to 10,7. And the direction of F12 would be the arctangent of negative 135 newtons over negative 350 newtons plus 180 degrees, since the X component is negative. And if we divide that out, I'm pretty sure that comes out to 0.39, but I was debating between 3.8 and 3.9. It's between the two, I'm sure, pretty sure. In any case, you can calculate it, but that's going to be the arctangent of 0.39 plus 180 degrees. Of course, you could take that arctangent and get an angle, but what we just want to see is we want to show that the R12 vector is equal and opposite to the force vector that we got here, which is going to lend a lot of credibility to the solution. The direction of the R12 vector then, corrected, and I've covered that up, but we did that a long time ago, is the arctangent of 5 over 13, not 13 over 5, 5 over 13, and 13 goes into 5, I'm pretty sure 0.38 times. There were some approximations in calculating these components. Coming out with a 0.39 here and a 0.38 here, makes these consistent. You can do the calculations with more significant figures and prove that to any number of significant figures, the two directions are equal and opposite. And they're equal and opposite because the arctangent of whatever this number is plus 180 degrees should be equal, is in the opposite, it is an angle that's 180 degrees opposite the arctangent of this angle, assuming this number and this number really are the same, and that proves that the two directions are indeed equal and opposite. One final comment, these directions came out equal and opposite. Why? In terms of this expression. Well, I've written it down here, but don't read it. Think about why the direction of F12 was equal but opposite to the direction of R12. Okay, R12 is in one direction, F12 is in the opposite direction, as we've established. Why is that? Well, hopefully you've thought of it. I'm not going to pause anymore. So pause now if you want to think about it and haven't. But it's because the KQ1, Q2 over R12 squared is negative. Okay, the directions came out opposite because this quantity was negative. And what makes this quantity negative? That's going to happen if and only if Q1 and Q2 are of opposite signs, which means then that F12 is going to be opposite to R12 anytime these are unlike charges, and that makes it a force of attraction consistent with what we know about the way like and unlike charges behave. Just to make sure we really understand this point here, what have we done? We've multiplied R12 by a negative, and that results in a vector in the opposite direction, the direction opposite R12. So that F12 is in the direction of R12. And since R12 goes from this point to that point, a vector back toward this point implies a force of attraction. And that happens if and only if Q1 and Q2 are unlike charges.